pull-up network consists of PMOS transistor and pull-down network consists of NMOS transistor. Here, initially the first operation is OR, so that whenever you are having plus operation, the PMOS transistor should be connected in parallel. Whenever you are having dot operation, the PMOS transistor should be connected in series. And here you can see that. So initially we are having plus operation, so that the PMOS transistor should be connected in series. And next, the pull down network, the NMOS transistor should be connected in parallel. So next, we're going to discuss signal strength. Here, signal strength is nothing but the strength of a signal. So, how close it approximates ideal voltage source. How close it approximate ideal voltage source. As we know that VDD and ground rails are strongest 1 and 0. So if it is VDD means its value is 1. If it is ground means its value is 0. So as we know that the NMOS pass strong 0 because it is connected to ground, but degraded or weak 1. And the PMOS pass strong 1 because it is connected to VDD, but degraded or weak 0. So because of this reason, we always prefer NMOS transistor for pull down networks. The NMOS pass strong 0 since it is connected to ground, and the PMOS pass strong 1 since it is connected to VDD. So next, we're going to see pass transistors. So here, the transistors can also be used as switches. The transistors can also be used as switches. So this is an NMOS transistor. This is an NMOS transistor and this is a PMOS transistor. So as I said, for the NMOS transistor, if G is equal to 0 means the transistor is off. When the transistor is off, there is an open circuit between source and drain. And if G is equal to 1 means the NMOS transistor is on. When the NMOS transistor is on, there is a closed circuit between source and drain. Similarly, for PMOS transistor, when we are giving 0, its complement is 1, the transistor is on, and there is a closed path between source to drain. And when G is equal to 1, 1 should be complemented to 0. It is open circuit between source and drain. Suppose, as we know that the NMOS transistor will be work only if its gate input is 1. So when the gate input is 1, if we pass 0, it should be a strong 0. If you pass 1, it is degraded for 1. And similarly for PMOS transistor, it should be on only its gate input is 0. Suppose if you are passing 0, it is degraded for 0. And if you are passing 1, it is strong for 1. Similarly, we will also going to discuss for transmission gates. So here the pass transistors produce degraded outputs. Even the transmission gates pass both 0 as well as 1. So transmission gates is nothing but it is a parallel combination of NMOS and PMOS transist that realizes a simple switch. So here you can see the transmission gate consists of a combination of NMOS as well as PMOS transistor that realizes or acts as a simple switch. So here, these are the various symbols of an transmission gate. Here, if you are passing G as 0 and GB is equal to 1, if you are passing here G as 0 and GB is equal to 1, So G is 0, it is connected to NMOS transistor, this is off. And GB is 1, when it is complemented, it is 0, even the PMOS transistor is also off. When both transistor is off, there is a open circuit between A and B, because both NMOS and PMOS transistor is off. Whenever both the transistor is off, then there is an open circuit between A and B. Next, suppose if G is equal to 1, which means, so whenever you are passing G is equal to NMOS transistor, it is on. And GB is equal to 0, its complement is 1. Both the transistor will be on. At that time, there is a closed path between A to B. So here the condition is, if G is equal to 1 and GB is equal to 0, the transmission gates works only if the gate input G is equal to 1 and GB is equal to 0. If you are passing 0, it becomes strong 0. If you are passing 1, it becomes strong 1. And next, we will also going to discuss about tri-states. Tri-states is nothing but it is having 3 states. Apart from input and output, we are also having one more state called as enable state. Here, the condition for this tri-state is, here you can see the various symbol of this tri-states. So, if enable is 1, then only the output Y equals to the input A. If the enable is 0, the output is high impedance. So here the tri-state will work only if enable value is 1. So here you can see that the operation of this tri-state is, so when enable is 1, whatever the input you are giving at the A, the same input will be passed to output. Whenever you are giving enable as 0, the output is high impedance. So tri-state means it has 3 states. Apart from input, we are also having one more state. We can call it as enable state. If the enable input is 1, then only the circuit will work. Whatever the input we are giving, that will be passed to the output. When enable is 0, irrespective of the input, the output is high impedance. We can also call it as Z. So next we're going to discuss about non-restoring tri-state. So here you can see that we are having input as A, output as Y, along with we are also having enable as well as enable bar. So here the transmission gate, which acts as a tri-state buffer, and it only requires 2 transistors, but it is a non-restoring circuit. So when it is a non-restoring circuit, if the input is noise, the same noisy input will be passed to the output. So next, we're going to discuss about the tri-state inverter. So here, the tri-state inverter produces the restored output, and it also violates the conduction complement rule because we want a Z output. So here you need to remember one thing. So in tri-state, if the enable is 1, then only the circuit will work. Otherwise, we will get output has high impedance. So here you can see the first figure. The first figure shows the tri-state inverter. The output is actively driven from VD2 to ground, so that it is a restoring logic gate. If you observe the figure A, it shows that it is a tri-state inverter, and the output Y, which is actively driven from VDD or ground, so that it is a restoring logic gate, and it does not obey the conduction complement 0. And next, if you are giving enable is 0, if you are giving enable is 0, as I said previously, the circuit will work only if enable is 1. So here, whenever you are giving enable is 0, both transistors are of open circuit. So the output is high impedance. And whenever you are giving enable as 1, both transistor will be on and we will going to get the output as A bar. And these are the various circuit symbols of tri-state inverter. So next, we're going to discuss about the multiplexer. So here, the figure shows the 2:1 multiplexer. The figure shows 2:1 multiplexer. Here we are having two inputs, D0 and D1. We are also having one more input, that is select signal, and we are having one output, that is Y. Here, a multiplexer chooses the output from several inputs based on the select signal. So based on the select signal, the output chooses among several inputs. So here we are having select signal, yes, the inputs of D1 and D0, and the output is Y. So here a 2:1 multiplexer chooses the output from the several inputs based on select signal. Suppose if the input D0 will be chosen, the input D0 will be chosen when the select is 0, and the input D1 will be chosen when the select is 1. The select signal will choose D0 when its value is 0. If the select signal value is 1, then we'll going to choose input as D1. So here you can observe. So when select signal is 0, it will going to choose D0 as input, so that the output is 0. If select signal is 0 and D0 is 1, the output is 1. Okay, the D0 will be chosen when select signal as 0 values. And D1 will be chosen when the select signal is D1 values. When select signal is 1, 1, if the D1 is 0, the output is also 0. When the select signal is 1, if the D1 is 1, the output is also 1. This is how the operation of a multiplexer. Okay. This is for the day. The remaining things I'll be continued in next class.